going to talk about probability. And before you take, if you go on to statistics, advanced statistics, believe it or not, advanced statistics is offered in a lot of the MBA schools, the top business schools, and it's a function of accounting. So you go through accounting. We consider the most complicated part of it is using the data to forecast business conditions in the future, or any kind of forecast in the future. But I had a friend whose son was going to Wharton School of Business, which is one of the top business schools in the world, and the way they eliminate people really is through the math. And so the top business schools require 3 semesters of engineering, calculus engineering. I was surprised. Very advanced mathematics. That was just on the analytical part. That was just on the calculus part. The other part was what they were requiring for statistical analysis was amazing. So a lot of the top business schools it's statistics and hardcore mathematics that eliminates people. But if you make it through, you get instantly high-paying job from those universities, of course. A lot of the other MBAs are kind of watered down, but everything has its place, I suppose. So let's talk about probability theory now. Probability theory, if you take probability, or they call it stochastic processes, then you really should, had calculus first. So this course is always fun because I have to try to tie it together without any calculus. And that's why I do these drawings and stuff, because unless you have the calculus, you don't really see the course kind of come together, except by what I'm trying to do. So they're just giving you a flavor now, but I'm showing you the place of it is there. And there are distributions being discovered, all the time. There's a distribution that's been in play for a while now that can detect forgeries on tests. A forgery, let's say, on check writing. For example, it turns out that the distribution of numbers that we use is heavily dependent on number 1, number 2, the probability of a 1 being used in any check. A 1 or a 2, right? It starts dropping off significantly. And a lot of people don't know, when they forge a check, they don't use 1 and 2s very much. They actually don't. They try to use 9s or something with bigger amounts, right? So as a matter of fact, there's a pattern to forgery that, unless you're aware of it, it can scan among many checks, and then they start saying, wait a minute, this is a set that looks a little unusual, a dearth of 1s and 2s, for example. So there's this underlying structure in almost every process that we do. We've had big satellites looking into outer space. We have the Arecibo, huge, and it's really a parabolic dish in a mountain, and it's been listening for aliens, outer space aliens for years, and they used to, looking for a pattern. Up to recently, they found no real structure, and they had it with SETI so that you could use your own computer when in downtime to help process all the data that it's receiving from outer space. But since then, China has built even a bigger one, the biggest in the world now, and they've received some unusual pulses that seem to be organized. And so, I don't know. We don't know yet, but Stephen Hawking was warning that maybe we shouldn't be sending out what was basically like an invitation. So I don't know if you heard about the little cards that they've sent out of space, are like little business cards, except that we're Earthlings, and they've been propelled into space with lasers. So they were basically announcing or pamphleteering throughout the space. He's warning that, well, maybe these people are, who they are not friendly. And my thinking is that, there's always this question, what's the probability of that there's life in another planet? There's a calculation that we can do that probability and calculate that there's life in some other planet. Of course, you have to distinguish it what kind of life. If you have an alien in my opinion, that has the technology to come to here, that the probability that they exist, and they have that type of technology where I think it'd be some sort of interdimensional travel. This is, if you take space and you can fold it, then you can have a shortcut jumping from one side to the other. So it turns out, according to Einstein's theory of general relativity, if you put a large mass on a plane where this is distance and this is time, it will push an indenture. It will warp space-time. In other words, mass warps space-time. So if you imagine a mattress, and the mattress is set up like this. I'm just giving you a kind of a broad sense of where we're using statistics and probability. And then I'll start into the probability. But in this case, is everybody done with the test? Or are you still working? Everybody done? Okay, I can turn this off. Maybe if you're not, you can. Who? Can you see okay? No? All right, here. Tell me when you're done. In the meantime, I'll just draw here right with a marker. At first. Okay. So, probabilities of things occurring. Okay. So if this were, let's say, okay, let's just talk about space-time. A lot of you probably know about space-time, but others may have not be familiar with it. But everything has to be looked at now, according to Einstein, through space-time. And so if this is distance, okay, some kind of displacement, I'm going to call it distance, and this is time. All right, so let's say I'm the center of all things right here. All right, and now time is moving on. Now my distance from me to this gentleman is fixed, this distance between here and here. So I'm at the origin. And let's say he's right about this far away from me, okay? And all of you are a certain distance away from me. Huh? But in time, we're still moving. So even though, I mean, the Earth is moving, right? Not only is the Earth spinning, right? It's spinning, but it's also, moving around a gigantic sun. So this has caused even a bigger indenture, and we're stuck in that indenture, and the moon is stuck around our indenture of the space-time mattress. So what happens is this. So as time goes, you know that this is spinning, and it's moving in a helix form around the sun as the sun is expanding out too. So everything's expanding. It's moving out. In the meantime, we're like expanding with it as a helix, right? So my point is, even though he's that far away from me, we are moving in time. So here I am, moving in time, yes. I don't know if you can see that, but he too is moving parallel with me in space-time, even though we're not moving from each other yet. But another second has gone by. This is how you have to think in terms of space-time. All right, so what is a black hole? As you think it's actually a hole, it's not. It's a hole in space-time. That gravitational thing of the planet is so dense that it pulls down, puts an indenture like a huge funnel that goes down really steeply. And in that sense, the gravitational is so strong that in space-time, light can't escape. Well, it can't escape its surface, but you have to look at it more into space-time than look at just a black hole, like it's a hole. It's not a hole. It's a very dense thing that has warped space-time down to almost like a singularity, they call it. From there's all sorts of estimates that go on, but anyhow, this is space-time, okay? So this is what Galileo discovered roughly 500 years ago or more further. He said, look, nobody knew it. But when I let's say the distance between here and here, right? I'm going to let it fall. Okay? You think, that it went, let's say it fell pretty much, or even if I threw it up, yes, with a certain velocity. It goes up, gravity takes a hold, it pulls down, right? It hasn't moved anywhere from where I threw it up. It's gone just straight up and down, right? Somebody say, yeah. Okay, so, but not in space-time. Let's say I throw it up. But when I throw it up, time is moving, and then it falls. Everything that's under a gravitational field falls parabolically. That's why when you look at the function y equals x squared, it's, plus 2, let's say something, ax plus b, you have trajectories of firing a cannonball or a bullet, whatever. I mean, or just throwing something up in the air and coming down. You're not supposed to look at it like this would be the distance, yes? Go up and down, yeah? But now I'm talking time. You getting the feel? So in algebra, you were doing factorization. Remember all that factorization that you were doing? Really was about finding these x-intercepts by setting the function equal to 0 and factoring. I think if you remember any of that from college algebra, right? But you may not realize how pervasive this parabolic curve is. It also has a unique thing because it has a focal point so that any rays or any kind of magnetic field that bounce will automatically bounce into the focus as it comes back. And believe it or not, that's how your headlights are, but this way. So your headlamp would have like a filament, right? And then there's your parabolic shape, right? It's kind of like this. It bounces and goes in reverse so that it focuses the light bulb in the direction that you want. Anyway, that's the parabolic dish, and that was Galileo that figured out that things fall in terms of space-time, right? But it was Einstein that said, look, mass distorts it. Oh. Now, all of this has led to quantum mechanics eventually. Now, I'm not sure if any of you have a feel for quantum mechanics? I don't know that there are 10 people in the county that might. I can give you a feel for it if you're so inclined, but the point is this, is that matter has two states. It's either in like a wave or like a particle, right? And guess what shape that wave is it's traveling across? Any ideas? In quantum mechanics, you can either be, matter has a duality to it. It can either be as a particle or more like a wave. And the phenomena was discovering that it can be either state. And not just everything, matter, everything. That means if you don't consciously look at something, it's kind of in a fuzzy state. Anyway, I can tell you. Anyhow, that wave that's traveling, so let's say I shoot a photon, right? I shoot a photon. Nature stops us from knowing everything about it. We either know the direction, but we don't know the position. It's one of the two. It's called the uncertainty theorem. That wave that travels across is nothing less than a bell curve. Quantum mechanics is, by its fundamental nature, statistical. And that was hard for scientists to accept because there's this spookiness as a distance, they call it. You see, with Newton, his physics was deterministic. That means if you had a billiard table and you had a ball here and another ball here and you shot it with the cue stick and you know the angle and the velocity at which you hit that ball and the force that it's traveling with, you'll know the trajectory after it hits with a certainty. Basically, I mean, there's no statistics in there, right? If you know everything going into a black box and then you know what's coming out with perfect prediction, if you knew everything's coming in, this is how we were thinking as scientists. You follow me? Imagine the break from that now into quantum mechanics, where Bohr's model was saying to Einstein, no, at the very small, of the things, the particles, the subatomic particles, things act not like intuitive at all. It's all random. It's all a probability of being somewhere, someplace. So in that case, even probability works. It's the only thing. So what it's saying is that fundamentally nature is probabilistic. It can happen or not happen, and it can be in two places at once. So if that's not weird enough, but the wave comes here, so I think everybody ought to have a little feel for quantum mechanics. So there's this thing that you can look at YouTube too. It's called a slit, double slit experiment. This is what set every. This is what gave us a break from Newton's into quantum mechanics. And I'm going to see if you guys can. I'm going to give you a little flavor of it, just so that you don't go through life without knowing anything. Because now we have quantum computing. Okay, with quantum computing, the idea is what we call supersymmetry. So if I can be in two places at once, then if I shake his hand, this is parallel processing, then under supersymmetry I can shake all your hands at once. That's parallel processing in quantum. If you can imagine how that could speed things up whenever parallel processes is required in quantum computers. And they're using the fact that you can be two states. It can be 0 or 1, and it can be a fuzzy state, a maybe in between, meaning it can be both 0 and 1 at the same time. That's quite a quantum mechanics. If it blows your mind too much, put a helmet on or something, because it's going to be, I'm going to show you the probability of statistics as it comes in, even in this level. And those of you who have no idea about quantum mechanics, this should give you a flavor of how far advanced, how far out there physics is now. So supposing you have a rifle, okay, and you're going to shoot, and you're pretty far away back, and you shoot one bullet at a time. So here comes the bullet, and it's traveling, and this is a metal plate with two slits fairly close together, depending on the later on how fast you're shooting, the frequency. Okay, so it's one bullet. Okay, and back here you have a wall. You know, the wall is supposed to will catch the bullets, whichever bullet comes through. Do you see? I don't know if you can understand, but if I shoot, do you see that the bullet would hit here? If it doesn't hit the slit, it bounces off somewhere else, right? So only the ones that are like perfect shots, these are same length. Like, you know, some of them will get through the crack, right? Slit, yes? Anybody? You assume not all of them are going to get through, right? Unless you're a perfect. Okay, so what I'm asking you is what kind of. Let's say you start shooting now thousands of bullets, one at a time. What would you expect to see on the back wall? Huh? Two slits, I would think, because the bullets that did go through would start making pock marks. Pretty much like two slits. You agree? Okay, so here was the first problem. When they change this now, this guy now has laser, and he's now, instead of a bullet, switching a photon, which is one of the basic elements. And he starts shooting, instead of bullets, now he's shooting photons, okay? And he shoots through the same slits. And this is not what happens. What happens is this. You start developing a series of lines that are equally spaced. Now that blew everybody's mind. Like, why should matter change as it's traveling across? Why isn't it just two slits? Why is it so many slits? And the only thing that would leave this kind of pattern is pretty much if you keep, you know, they're like, you know, they're pockmarks, right? Turns out to be a wave. And so what happens is, say this bullet now turns into a wave. That was really weird. And that wave is the normal probability. And this being the highest chance of getting through, you know. So it's traveling, if you could imagine this wave traveling, a normal curve, a bell curve, traveling, okay? But think of it as a way a wave would work. Okay, so now let's suppose that now I have this plate here, okay? And I'm looking at the top. So here's a slit, the very top, yes? Anybody? Okay, and here comes the wave. It's hard to think of matter as just a density, probability of it being. That's what we're doing. It's a probability that this point is anywhere around here. It's actually calculating all possible paths to get through there. You could have a freak path come out here, get hit by a neutrino from outer space, and bounce it back into the slit. It's possible. So that's why it becomes less and less probable, but it's still possible. See how much different that is than hitting a ball, knowing the force and the direction when it hits the resultant. Because we thought physics was done. Well, this screwed us all up. Where did this come from? Well, it started from, the Germans asked to find the electric light bulb was just coming out, and they wanted to find a filament that would give, the most light for the least amount of energy. And this is where it all started. But anyway, this thing goes here. Now look what happens when this wave travels. When this wave finally hits these two slits, yeah? Guess what happens? So when that wave hits, it forms two wavelets as they come through, as the wave comes through. Do you see that? It's, when you throw two pebbles in a pond. Do you see it? Okay, so what happens is this. So all of a sudden when the wave hits, you're going to have little ripples like this. You see? You see? And then this has little ripples. So it will go like this. And it will go like this, and like this, and like this, and like this, and like this. You see it? So what happens, you have two waves now. The one went into two. And so what happens here is that when you have a wave and it hits, or here where they're intersecting, if they hit a wave and they're both plus, you're going to get the brightest spot, right? And it's because where they're intersecting here, that's what finally hits on the back of the wall. And that's why we know it's traveling as a wave. Cool? All right, now it gets really weird, so hold on. This is quantum mechanics. This is probability statistics, okay? What the implication is that at the very small, it's possible to be at two places at once. That's your fuzzy set in quantum mechanics. Now, that's strange enough. The fact that matter is energy, right? E equals mc squared. So matter just can yield energy by a factor of light squared. So all of this is saying is that it behaves as a smear. Matter is a smear until it hits, yeah? And then it goes into these things here, right? And then when it hits the back wall, it makes that interference pattern we're talking about, not just two slits. Okay? So, guess what happened? We were expecting just two slits like when we were shooting the whole bullet, yeah? So when scientists tried to put a monitor here to kind of detect, to see exactly, if it's going more into one or other, believe me, this screws up logic, right? Because if A causes B and causes C, then we say A through the transitive property through B causes C. It's causality. But when you can be in two places at once, that means time can pop forward and backwards for a little small time in a little thing. It's all scrambled. It's fuzzy. And nature won't let us understand it at this moment. When you try, get this. This is it. This is what you've been living for. When you try to figure out what's going on, this wave collapses back into a particle, a quantum. It knows what you're trying to do. And this is what's blowing everybody's mind. Because because you have a consciousness, it seems to be affecting the outcome of the... So when you actually try to figure out what's going on, all of this changes back to just two slits, as though it was a single point particle. Does anybody, you know what I'm saying? The phenomena is that anybody who has a consciousness seems to be entangled with the experiment. That's why Einstein didn't like it. It's spooking us at a distance. He said God doesn't play dice with the universe. Actually, he does. It's probabilistic, if you believe in God. It's probabilistic, and only when you try to figure it out, there's this uncertainty theorem, uncertainty principle says nature will not allow you, not at that level, to figure out what's going on. Because as it goes to the slit, you have better and better idea where it's located, right? But you have less idea of the direction it's going. You cannot know both. This is really, really weird. And what's more weird is like this idea that we just have sensors here, right? If you look through a microscope and you're shooting a photon down and you're looking at the sample, right? It could be that the sample's so small that the photon itself is moving it, right? There's no photon here that we're moving. We just set up some sensors. How does something inanimate know that that's what we're doing ahead of time? And only when you look at it, and only when you try to figure out what it's doing, does it collapse. So the probability field collapses back to a bullet. The implication is that everything behind me, let's say, is not really fixed until I look at it constantly. This doesn't work at the big scale. I'm talking about the atomic, right? The big scale, we don't notice the effect. We're in the big world. But here we do. And it has implications all over with communications and so forth. So there you go. I just give you a kind of thing. Now, what if you brought a dog in? Could a dog be enough consciousness where they'd say it's figured out too? I don't know. There are scientists that are saying that even by chance, if you could figure out, the more you know where it's going through and you can figure out where it's going to land, because as a wave, it could land here, 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 or here, right? So as that wave goes through, I wonder, like, well, at this point where they had to come up with the theory of duality, that all matter, not just light, all matter at its basic constituents is dualistic between a wave and a particle. Nobody understands it. Nobody really understands quantum mechanics. You just learn to accept it. That's how reality is. And and by my thinking, given that I'm teaching statistics, I think everybody should get a flavor for it, for quantum mechanics. And even though it's pretty weird, it seems to be, there was a 10-year debate, and it seems to have won out over a deterministic world, right? In fact, on YouTube, you can find Stanford University sending a beam of photons with a laser, and they only have one slit. But the slit has a gate, so you can start tightening up the slit. Imagine that you have sort of a gate, and here you have, as you turn it, you can make it even more and more and more narrow, yes? So as the photon goes back, if we're not trying to figure out what it's doing, it'll be it'll be more like a spread. It says only one. It's not interfering with itself, but still, this whole place lights up. Okay? So what I'm saying is that as you tighten it, right, you would expect, as this got narrower, for the light beam hitting the back wall to get smaller, wouldn't you? Because you're cutting it down. No, it gets bigger. Because you know more and more information about where it's going through, it's going to give you less and less of the direction. And that's reality as far as we know right now. And believe it or not, this theory later on leads to what they call a multiverse possibility. But I don't want to blow your minds too much. Anyhow, I read in that if by chance you guess, okay, you guess where it's going to hit. So you say, I think it's going to hit here constantly. And you happen to be right. Nature will pull back time for an instant of a second and rerun it so that it'll come out wrong. That's what they say. And I think that's kind of weird. But the whole thing's kind of odd. But what we consider to be reality now is based on this quantum. And because I can be in two places at once, we're trying to use that in quantum computing. That's the time when I shook his hand, I shook all your hands at the same time. Parallel processing. Okay. Any questions? Time? It's good to know, I think. Okay. Now, let's talk about the probability. And let's talk about what an event is. So you remember that I'm going to call this our sample space, as in the quiz, the sample side, right? And then we have a collection of observations, x of 1, x of 2, x of 3, right, x of 4, and up till our last observation, x of n. And where did we get these observations? Where? Where did we pull? This is our sample. Where did we pull those observations? From a population. And how did we pull it from the population? Some sort of random sample, yes? Okay, now, but we could call a subset of these an event. If we choose, we can call this event A and event B. All right? So let's start with the very basics. Let's talk about just event A. Okay? So now I say, so we have probability A. So what is not in A is A not. Got it? So I'm saying that if you take the probability of A occurring, this event, plus the probability of A not occurring, that has to be equal to 100% because that's your whole sample space. Yes? Yeah. That would be for X. This does. It is a little confusing, but we use it as A not. It does maybe a little bit confusing, but in this case, I'm talking about. No. So it's either the probability A or A not. And now I'm talking about a group of an event. Do you agree? So this lends itself to a lot of homework problems that you can solve by knowing this. This is called a complement. Now I can say that P of A, right? That the probability of A can be equal to 1 minus the probability of A not happening. So sometimes it's easier to calculate this than to try to calculate your event. Find a calculate of it not happening. Are we okay with this? Good. Okay. So that's it. Now I'm going to take, instead of putting A not, I'm going to have another event called B. All right. Now here's something we have to understand. If you have event A and event B, and this is called a Venn diagram. If you notice, there's no intersection, right? So if I want to talk about the probability of A or B happening, you see it? Then if there is no intersection, right, then it's going to be equal to the addition rule of probability, which is the probability of A plus the probability of B. Because there's no intersection. These two events are called, they are mutually exclusive. You hear that term all the time. That means there is no intersection. Do you agree? Okay. However, suppose that they shared some observations so that we have B and we have A. So this thing is called event B, and this is the intersection of A and B. I'm sure you've seen this before, right? In elementary and whatever. This is the Venn diagram. So now now I want you to know that OR can be written mathematically in different ways. So I can write the probability of A, and then I use this U like this. Actually, let me just use this now. I know I get the light. I don't know why I'm not using it. Let me get this why I'm not using this. Oh, make it easier. Anyway. Okay, let's see if I get this. Okay, that must have been way back. Okay, so what I'm saying is that the probability of A or B is written in logic format like this. The symbol, I think you've seen it before, A, and this upside down yard means OR. Okay? And you have P and A and B. That was the intersection, correct? Remember in the Venn diagram? And this, in a logic symbol, can be written like this. The probability of A and B. Okay? I know you've seen this before. This is or and. Okay? Now, in the case of or, make sure you got it right. In the make sure of or, you must check to see if they are mutually exclusive. Okay, you must check because, okay, and so let me show you. So if we have it like this, where you have event A, and event B, okay, now we have an intersection. Okay, so what's happening is that I'm going to say, I'm asking now, if I ask what is P, the probability of A or B occurring, yes? Well, it's true that it's going to be equal to the probability of A plus the probability of B. That is the addition rule of probability, but because we have an intersection, we've added the intersection twice. We took this area plus this area, right, and where they overlap. So we have to subtract the probability of A and B. All right? I'll give anybody extra credit if they want to do this. Find that same equation for this. A, B, and C.
So what do you do that? C, P, C, add that in the multiplication.
Well, you're gonna have the probability A plus the probability.
You got to subtract out of with the C too.
Yeah, but what would you have to subtract? This one's, the intersection of A and B. This one's the intersection of this, and this is the intersection of all three. So you got it? So, just play with it and just see if you can get it. It's the same thing. Obviously, it's going to be a lot longer because you're going to have to subtract every intersection plus the center intersection of all three of them. Huh?
Would you call it D?
The intersection? You could, or you could call it this intersection here, like, you could call it the probability of A and B and C. And this part right here, see it? Just that piece?
So that plus
Yes.
plus
Subtract. Yeah. And this intersection is the probability of A and C. Well, oh, really? I never thought it was honey, but it's okay. I mean, I don't see the humor in it, but everybody is different. Okay, now, this is called the addition rule of probability. We need this to get to where we're finally doing our hypothesis testing. That's why we need probability. It seems to be out of place. It's another factor that we need to go in to do the hypothesis testing. It doesn't change anything what you took on the quiz. I'm just showing you how the mechanics of it is going to happen. Okay, so with the addition rule, you must check for whether there's an intersection or not. If there's no intersection, it's called mutually exclusive. Any questions there? No? Okay, now let's talk about intersection. That's the multiplication rule. This one's a little more subtle. Students have more difficulty on this particular thing. So let's take a look at it here. Now I'm talking about what they call this is the addition rule, right? Here's or, and here's minus the intersection. I don't know if you can see it in the text itself. Let me make this a little bit bigger. No, I can't do it there. Oh, yes, I can do it here, huh? Let's see. Okay, here's what I just got through writing, right? Let me ask you, if the two events are mutually exclusive, what is the value of the intersection? If the two events are mutually exclusive, what is their intersection? What's the probability of their intersection? Huh? What does mutually exclusive mean? They're exclusive of each other. Exclusive, mutually exclusive. That means there's no intersection. If there's no intersection, what's the probability of being an intersection? Yes. So if it's mutually exclusive, that's all it is, the addition of the probabilities. If it's not mutually exclusive, it must have an intersection. Right? You should see that. This is what determines whether it's zero or not, is whether it has an intersection, okay? Now, we have the multiplication rule. The multiplication rule, remember now, this is talking about the intersection of A and B. Now, the problem with drawing it, and if I draw this in terms of A or B, Okay? There's another concept that we have to put under our belt. When we're talking about, yeah. Oh, you do already? Well, you can turn it in afterwards. Okay, now we got A and B, yeah? Somebody say yeah.
Yeah.
Okay, but now I'm talking about not or, but and. Okay, so now I have to tell them a concept called statistical independence. Okay? It's something like mutually exclusive, but you can't tell by looking. All right? I'm going to give you an example. Suppose I ask you, what is the probability of getting a one-eyed jack, or say a black jack of spades? What is the probability out of a deck of cards? Yeah, well, that would be black. I'm talking about a black jack with one eye. All right, if you want to do just the blacks, let's say 2 out of 52 now. So let's say that I could bring a deck of cards to you, and you pull out a card, right? And you're thinking, okay, I want to draw twice. I'm going to draw A to see if it's a jack, and then I want to draw another card, okay? Now the question is, do I replace the first card that I pulled out? If I take the card, I pull it, and before I draw my next card, I put it back in the deck, that's called replacement. Okay? If you have replacement, okay, so now that means if you're replacing the card to draw the second draw, that means these two events are statistically independent. One is not affecting the other. If you take a draw from the card and you don't return it, guess what? You've just affected the next one. Because this will be 1 out of 52, right? But over here, our base is down to 51. Does anybody know what I'm talking about? If you don't replace it, right, your sample size has gone down by 1. In that case, because you didn't replace event A, the act of drawing event A has affected the outcome of a probability of B. Does anybody follow that? Okay, and let's say in the case, it's something similar, right, but I can't really show it like I could with mutually exclusive. One has to now look at the experiment itself and see if it's requiring replacement or not. Okay, let's suppose that it is independent. Let's say yes. In that case, the probability of A and B simply becomes the probability of A times the probability of B. It looks a lot similar like the addition rule, doesn't it? Except we're not adding, we're multiplying. Now, what do we do in the case where it is dependent, not independent? This is independent. Right? Now, what if it's dependent? That is, I'm not replacing it, right? Then we write it like this. This is the probability of A occurring. Yeah? And then we have the probability of B. Okay? And we put a vertical bar, it means given. Write the word given. That A has affected B. Do you see the difference? Now, you don't know what that means yet, but the way to read it is this is the probability A times the probability B, given that probability of A affects probability B. Yeah? Do you have a question? No. Okay. Do you understand what I'm saying? This is showing no replacement. This is probability of B, given that A, we didn't do any replacement with A. So that A, the event A, will affect the probability of B. Does anybody see what I'm getting at? Do you see it's kind of similar to the addition rule of not mutually exclusive, right? That's when you have this thing here. See it? Somebody say, I see that. Okay, so I want you to understand now, mathematically, how do we write this thing? So let me put over here, you might want to take a note that this the probability of B given A is equal,
So like the given A would be the taking one out, right? That changes
and not replacing it.
and not replacing it.
Yeah. You know, if it's a case where, you know, you replaced it, then it goes back to this. The probability A times probability B. If you replace the card. If you don't, then what happened in A affects what the outcome of B is going to be. Are we okay? All right. So what I'm saying is this is going to be equal as the probability of A and probability of B, or probability of B, divided by the probability of A. So wait a minute, let me write it like this so you see this. I have the probability of A and B divided by the probability of A. That's what this means. So you would take the probability of A and B and divide it by the probability of A. And this would give you this. Now you have P of A. You see? Take this answer, goes in here. And now you have there. So you need to know that the probability of B given A is equal to the probability of A and B given B. This is called a conditional probability. Why? Because this is conditional on this event. So you can see that dependence and independence is sort of subtle. You can't see it from the Venn diagram. You're going to have to look at the problem itself to figure out the way the problem is worded, whether or not these are independent events or not. And yes, you mean, are you talking about this? Yeah, that's probability of A. Okay? Look what happens. Look what happens. What happens if this event is independent? Then what can we do? We can write this as what? The top part. Let's say it is independent. So let's go right here. All right? So let me rewrite this. So I'm going to write it like this, okay? This is a probability of A, yes? And now the probability of B given A. Yes? Okay, now I'm going to rewrite this guy as that. All right? So I'm going to write it as P of A and B given that the probability of A has affected it. All right? Do you see what I did? I just replaced this with the definition of this. Say yeah.
Yes.
Okay, now, if it were actually independent, yes, then we could write it like this. If it's the case, even though you write this, it's okay. And you find out that they're independent events, how can I rewrite this thing here, the top part? Yeah. Huh? Oh, it's time? Well, let me just, how can you write that top part? Anybody? Like this. Do you see that? So that would end up to being what? The probability of A times the probability of A times the probability of B. You see? Divided by the probability of A. Divided by the probability of A. And guess what? That divides out, and you're back to the case of independence. Okay. Then let there be light. Thanks. Good. Thank you. Okay, good. Yeah. Thank you. That was fast. I got a feeling it came off the internet. Good, thank you. No, that's okay. Well, that's a nice big piece of paper. I remember when I was in elementary school, my father bought me a kind of a notebook, but it was not the regular like yours. But when I went to school, they failed me because I used that paper. Idiots.
Here's mine. No, stuff like that done.
These are your homework?
Yep.
Okay.
3.1 right
All right, great. Hee 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 hee. Going to the computer? Are you going to the computer room? Yeah. I'll send you there.